Hello, and welcome back to the Cracking Fang YouTube channel. Today we're going to be solving LeetCode problem 1570, dot product of two sparse vectors. You're probably wondering why I'm making this video. If you look on LeetCode, this question has a 90% acceptance rate, so it can't really be that hard. Why am I wasting my time making this video? Well, there is a right way to solve this question, and there is a wrong way to solve this question. And most people solve this question the wrong way, and if you try to solve it that way in an interview, you're probably not going to pass, or your interviewer is going to hit you with a follow-up that you're not going to know how to solve. So let's walk through this question, and I'll tell you how to solve it if you get it in a real interview, and not just how you would solve it on LeetCode to get, submission accepted, because that's not the same as actually passing the interview and getting the job. So let's jump right in. Let's read the question prompt. Given two sparse vectors, compute their dot product. Implement the sparse vector class. Sparse vector will take nums and initialize the object sparse vector with the vector nums. It also has a method dot product, which will compute the dot product between the instance of sparse vector and vec. A sparse vector is a vector that has mostly zero values, and you should store the sparse vector efficiently and compute the dot product between the two sparse vectors. Follow up, what if only one of the vectors is sparse? Now, again, this is the case of LeetCode explanations being absolutely terrible, having zero proofreading, and they should really get a native English speaker to write these. What this question is basically telling you is that it wants you to implement the sparse vector class. And you need to set up the initialization function, so your init function if you're working in Python, or I guess this is your constructor in Java and C++. Set it up, store the vector of numbers that you're given, and then you have another method which is going to be called dot product. And what this is going to do is it's going to take another sparse vector class, and it wants you to compute the dot product between the numbers that you have for the first sparse vector that you were given, and then the new one that you were just provided in dot product. So that's how the function is given to you, and I really wish LeetCode proofread these, but sometimes they don't. Before we get into the solutions, let's recall how we actually compute a dot product. And for this example, we're going to use non-sparse vectors just to illustrate this. So we have vector 1, which is 1, 2, 3, 4, 5, and we have vector 2, which is 6, 7, 8, 9, 10. So how do we compute the dot product? Well, if you remember, what we do for a dot product is we basically pair up indices and we multiply the values there, and we add up, all of those multiplications to get the dot product. So for example, index 0 in vector 1 has the value 1, and index 0 in vector 2 has the value 6. So we multiply those and we get 6. And then we add to that whatever is at the next index, so 2 in vector 1 and 7 here, so we multiply that. So we have 6 plus 14 plus, so then here we have 3 in vector 1, and we multiply that with whatever is at the same index in vector 2, so 8, so plus 24. So then we do the same thing for the next index, so this is at index 3 here, so we have the value 4, and here we have 9, so we're going to add 36. We're going to do the same thing for the last index. So we're going to do 5 times 10, so that's 50. And when we add it all up, we can see that we get this value 130. So that's how we compute the dot product. Now, let's solve this question. And there's actually quite a few solutions here, so we'll walk through them one by one. Okay, we've read the question prompt, and we've gone over how to compute the dot product of two vectors. Now, let's start going through the solutions. The first solution, and what we can consider the naive solution, would be to do exactly what we did in the example. We're just going to take the numbers that sparse vector is initialized with, and we're just going to compute the dot product following the dot product formula without doing any sort of pre-processing. So if we were given vector 1 as 0, 1, 0, 0, 0, and vector 2 as 0, 0, 0, 2, what we want to do here is just compute the dot product. So let's do that. So obviously 0 and 0, this is going to be 0, plus 1 times 0, 0, plus 0 times 0, 0, plus 0 times 0 again, 0, plus 2 times 0, and then we get our final solution of 0. Now, what you'll probably notice here is that anytime we multiply by 0, the product is always going to be 0. So the reason that this is the naive solution is because anytime you have a 0 in one index, it doesn't matter what is in the index for the second vector, the product for that, index pairing will always be 0. So there's really no reason to store the entire vector, right? Because if one index has a value that is 0, then there's no point of storing, the value in the second index, because it's always their product is always going to be 0. It's simply inefficient to do that. So storing the vector directly is inefficient. So can we do better and actually not store the entirety of the array? And the answer is yes. And that's going to be our second solution, which we'll do right now. So we've seen the naive solution, and we've identified the issue with it, which is that we know that we have sparse vectors, and since the dot product is going to be the product of any two indices, the values there, if one of the values is 0, which we do have a high probability because it's a sparse vector and a lot of the indice values are going to be 0, then the product for that indice pairing is going to be 0. Therefore, there's no point of computing it or storing it because we're just wasting memory. Now, what if we only wanted the indices that don't have 0 values, right? So let's store somehow only the indexes whose values are non-zero. Well, the most straightforward way to do this, and what will allow us to compute things more efficiently later, is to use a hash map. So for example, instead of storing the entire array, what we want to do is we want to store a hash map. And the key is going to be an index, and the value is going to be a value that is non-zero. And we're only going to store indices that have non-zero values. So for example, in this first vector, if we were given 1, 0, 0, 2, 3, then we would only want to store the values for the indexes 0, 3, and 4, because those are non-zero. We don't care about the other ones because we know that they're 0. Therefore, anything they're multiplied by in the second vector will always be 0. We can just disregard it because adding 0 to our dot product is still going to be whatever this, the dot product we had before is, right? Adding 0 doesn't change whether we multiply or whether we add or subtract it. So what would that look like? So we would have, index 0 has value 1, index 3 has value 2, and index 4 has value 3. And we're going to do the same thing for the second vector. So we can see that at index 1, it has a value of 3, and at index 3, it has a value of 4. Cool. So now we have the two sparse vectors, and they're in a more memory efficient storage system, right? We're using hash maps, and this way we can cut down the amount of space we need because we are only storing values that can actually be used for computations. But now, it could be the case that in one vector it's non-zero, but in the other vector it is 0. So we still need to compute the dot product. So how are we going to do that? Well, we can go through the keys of one of the hash maps, and we can look it up in the second hash map. And if that key also exists in the second hash map, that means that both the maps have a value at that index that is non-zero. Therefore, we can multiply them together and then add that to our dot product. If the key doesn't exist in the other map, that means that the second vector did not have a non-zero element in that position. So for example, if we were to go through the keys and the values of vector 1, so we would start at 0 and 1, right? So we're going to say, okay, my key is 0. So does the key 0 exist in vector 2? We can see that it doesn't. So that means that vector 2 did not have a non-zero element at the 0th index, which we can verify because it is 0 here. Cool. So that means that there is no multiplication that we can do here. Then we move on to the next key. We're at this 3. So what we do, we look up 3. Is 3 in vector 2? Yes, it is, right? So vector 2 has a non-zero element at the third index, which is this 4 here. So that means that we can multiply the 2 from the first vector by the 4 in the second vector and add that to our dot product. So we see this 2 and 4, which is 8. And then we're at the last key in vector 1, and we're going to say, okay, it's 4. Is there a 4 in vector 2? We can see that there isn't. So that means that vector 2 did not have a non-zero element at the 4th index, which we can verify because obviously here it's 0. So That means that the only two things we could multiply were the 2 and the 4, so our dot product here is 8. Cool. So time complexity wise, we actually don't improve from the O of n solution that we had in the previous case. But space wise, this is still technically O of n in the case that our vectors aren't sparse, they're completely full. But this is more memory efficient because we're not storing zero values here, these index values. We don't have to worry about them. We're only storing a subset of our actual array. So it is more efficient. Though the runtime complexity is the same, in practice, it should be more efficient because we're dealing with sparse vectors. Now, if you submit this solution on LeetCode, it will work and it will be accepted. But where interviewers will actually push you is they'll ask you this follow-up. They'll say, okay, cool, so you've done the hash map solution and it works. Great. What if your hash function sucks? And this is where you could get caught out like a deer in headlights, because you have assumed, incorrectly so, that your hash function is efficient. We are taught that hash maps are constant time lookups, constant time insertions, but in reality, that is an assumption that isn't always true. Sometimes you're going to be working in a system that your hash function sucks. And since you're potentially doing a lot of insertions whenever you build the hash map, and then a lot of lookups when you're actually iterating through the hash map and then looking up the key in the second vector, if your hash function sucks, then a lot of the computation time for this problem is going to be spent just doing, the hashing function. So this isn't the best solution because you cannot assume that you have a good hash function. Now, do you have to assume this for every single LeetCode problem that you see, that using a dictionary isn't going to be constant time? No, this is just going to be a follow-up for this specific question, and your interviewer is going to want to push you to find a more optimal solution in the case that your hash function sucks. You can't always assume that you're going to have a really good one. So this is where we're going to need to move into the third solution, which is most likely what your interviewer is looking for and going to be the solution that you ideally want to implement in your interview. So let's go through it now. We discussed the naive solution, we discussed the hash map solution, and we've talked about the problems with both solutions. So what is the most optimal way to solve this problem? The best solution here is actually going to be the tuple solution, which combines the principles of the first solution and the second solution. So what do I mean by the tuple solution? Well, if we remember the issue with the hash map solution, it was that we could potentially have a hash map that was really bad. The benefit of using the hash map solution was that we were only storing and looking up values that we knew were non-zero. Therefore, the product could potentially be non-zero depending on whether or not the other value in the other index was non-zero as well. So how do we take the principles of the hash map solution but combine it with the first solution? Well, if you recall, what we did in the hash map solution was to basically build a map of all the values that were non-zero, right? And we're going to do the same thing for the tuple here, except we're not going to use a hash map. We're basically just going to have an array, and we're going to populate this array with pairings of index and value, where the value for that index is non-zero. So for example, if we had our vector 1 here, we could see that at index 0, it has a value that is non-zero, right? It's 1. So we would put that into our array. So we would store it as a tuple of 0, which is going to represent the index, and then the value, which is 1. And then we're going to go through the array. Okay, is index 1 non-zero? No, it's not. Is index 2 non-zero? No, it's not. Then we get to index 3, which is this 2 here. And we can say, okay, well, this is non-zero, so we'll put it in there. So for index 3, we have 2, and then we keep going. Okay, the value at index 4, is it non-zero? Yes, it's a 3. So we're going to put it into our kind of array here. And this is how we're going to store the sparse vector in the most efficient way possible. And we're going to do the same thing for vector 2. So we see that at index 0, it's 0, so we don't care about that index. and we see at index 1 it's 3, so we do care, so we're going to put it in index 1. It has a value of 3. Then we're going to keep going. Okay, index 2 is 0, we don't care about it. Then index 3, we see that it has a value of 4, which is non-zero, so we're going to put it into our our memory here, and we're going to say index 3 4, and then index 4 here is 0, so we don't care about it. Now when we want to compute the dot product, what we want to do is we want to use a two-pointer approach, where we're basically going to crawl the arrays, and we're going to check if the indexes line up. Then we're going to basically multiply the values, and if they don't, we're going to move whichever index is smaller forward. And this is a little bit confusing, and we'll go to the code editor to actually. So we've talked about the three solutions to this problem, and it's time to write the code for the most optimal one, which is going to be our tuple solution. Now I'll admit I did hand wave a bit when it came to the diagram portion, because it's going to be much easier for me to explain it as I go writing the code than it is for me to draw it out using my mouse on the editor. It's going to be painful for both of us, and it's going to be much simpler to explain it here in the code. So let's jump right in. Remember that the sparse vector class needs to be initialized, and it's going to be given to us a list of numbers. So what we want to do is we want to store this list of numbers efficiently. So remember what we said with the tuple solution is that we want to store an array of tuples where each tuple is going to be an index and a number pair where that number is non-zero. So basically we're only storing the numbers the indexes whose values are non-zero. So let's write that out. So we're going to say self.nums is going to be just an empty list start, and we're going to say for I num in enumerate nums, and enumerate is just syntactic sugar in Python to basically just give you the index and the number when you're iterating over a list. If you're doing this in C++ or Java, just set up a for loop and then just extract the values with the index. But this is Python, so I'm just going to use the tools available to me. So remember that we only want to store the tuple pairing if the number is non-zero. So we're going to say if num, so basically if the number is not 0, we're going to say self.nums.append the tuple with the current index and the number. Cool. So that's how we're going to populate our sparse vector. Now we need to actually compute the dot product of the two sparse vectors. So let's create a variable to store the dot product. And we're going to say that I equals j equals 0. So these are going to be the pointers that are going to represent our computation here. And this is going to help us crawl through the tuples. And I'm going to get rid of this bit here because we don't actually need it. So what we're going to do is we want to crawl through both of our arrays. So we're going to say while I is less than the length of, we can say self.nums, and j, that's going to represent the pointer for the vector that we're given. So while j is less than the length of vec.nums, we're going to say the index at the current I in the first vector, so I index and then I num, is going to be self.nums of I. And then we need to get the value in the second vector. So we're going to say that the j index and the j number equals to this is going to be vec.nums of j. Now what we need to do is, this is where it's a little bit complicated. Basically, we need to make sure that the indexes match, right? If the indexes match, then we need to multiply the two values. If they don't match, then we need to move whichever index is actually smaller forward, because we may not have reached that point in the processing yet. When we had the hash map solution, we could just look up the index directly, but this time we have a list of tuples, so we have to move our pointer forward or backward. No, backward, we can't go backwards. Forward, depending on which condition is met. So we're gonna say if the indexes match, so if I index equals j index, what we're gonna do is we're gonna say dot product. We're gonna add to it the product of the number at I, inum times jnum, right? So we're going to say I plus equals to 1, j plus equals to 1 in that case, because they were matching, so then we can move both the pointers for I and j up. Otherwise, if the index at I, corresponding to I, is actually greater than the one for j, then we're going to just move j up. Otherwise, we move I up. And at the end, what we want to do is return the dot product. So let's submit this to make sure that we haven't actually made a mistake somewhere, and we can fix it if we have, but it looks like jnum. Oh, whoops. Okay, so this should be jnum, and we should be good now. That's always takes a little bit to run. Cool. So our solution works. Now before we talk about time and space complexity, which we've already touched on a bit, let's walk through the example here to actually verify how our code is working, because it is a little bit unclear. So let's go through with actual variables so we can prove to you why it works. So let's do the initialization for our first nums here, right? So we're going to say, okay, we're only concerned with the non-zero values. So that means that at index 0, there's a 1. At index, let's see, what is that? 3, there's a 2. At index 4, there is a 3. And that's going to be our first vector. And our second vector is going to have at index 1 a value 3. And then at index 3 is going to have a 4. Cool, so we've now done the initialization for both the sparse vectors. Now let's do the dot product part, right? So our dot product is going to equal 0 in the beginning. And let's see, we have I equals 0, j equals 0. So that means, okay, so we need to do while I is less than length of self.nums. So this is going to be length of 3. And this is vec.nums is going to be this second vector here. So it's going to be length of 2. So we know that we're in the bounds here. So what is the I index and inum? So we're going to extract the values from whatever, self.nums of I is. So I index is going to be 0 and 1. And then for this j index, jnum, we're going to extract it from vec.nums, which is going to be the second vector here. So it's going to be 1 and 3. Now, this is the part where we compare the indices and check that they match. So we see that, okay, does the I index equal j index? No, because 0 does not equal to 1. That means that there is no matchup here. So we can't compute the dot product for this pair, which makes sense because obviously their indices don't match. And for the dot product, we always multiply where the indices match. So that means that nothing can happen here. Now, does I index, is it greater than j index? No, because 0 is not greater than 1, which means that we need to move I up by 1. So we move I up by 1, and now we go through our loop again. So I is still less than 3, and 0 is still less than 2, right? Because j is, j is 0, and we're still less than 2. Okay, so now we extract values again. So what is the value here at I index? So it's going to be the index 3, right? This is corresponding to the first index. So self.nums of I is this, so 3 and 2. And we're still j equals 0, so now we're at, it's going to still extract 1 and 3. Cool. So now, do these indices match? 1 and 3. No, they don't. So that means, again, we can't compute any sort of dot product. Now, is I index greater than j index? Yes, it is. 3 is greater than 1. So we want to move j up by 1. So now j becomes 1, and we go through our loop again. So is 1 less than 3? Yes, it is. Is 1 here for the j less than 2? Yes, it is. So that means that we can continue with our while loop. So we extract the values, and this time, since I didn't change, this is going to be the same, still 3 and 2. And now j is 1, so we extract 3 and 4 here. So we say 3, 4. And now we go through our if statements again. So does I index equal to j index here? Yes, so 3 equals 3. So that means that we have found a pair that are both non-zero and they have the same index. That means that we have to compute the dot product for them. So we're going to add to our dot product inum, which is 2, times jnum, which is 4. So we're going to add to our dot product 8, right? Because 2 times 4 is 8. So we're going to do that. So our dot product is 8. Now we move both I up by 1 and j up by 1. So now I equals 2, j equals 2. So is I, which is 2, less than 3? Yes, it is. And is j, which is 2, less than 2? No, it's not. It's equal to 2. So that means that we have exhausted one of our vectors and we can actually stop. So we're done, right? Because now this while loop breaks, we don't have anything left to do. So now we can just return the dot product, which is 8. And that is our solution, as we can see here. So that's how you're going to solve it. That's the algorithm. Hopefully it makes a little bit of sense. It is a little bit confusing at times because you're working with that 2-pointer approach, and then you have like pointers here, but then you have indexes in here, and it is a little bit confusing, but just kind of look through the example again, think about how it works, and it'll definitely click for you. Let's think about the time and space complexity. Well, if we look at this initialization function, we have to go through the entirety of nums once from left to right to basically parse out the values that we need to store. So, in this case, what's going to happen is that it's going to take, linear time to go from left to right and parse these things out. So that is the time complexity of our init function. And then for space complexity, in the worst case, we would be given a vector that isn't sparse. So that means we have to store the entirety of it. So that means in the worst case, it would be an O of n space solution. Now for the dot product, in the worst case, we would have 2 fully non-sparse vectors. That means that every single element is present in both the arrays. So what's going to happen, and in this case, since they're equal lengths here as part of the constraints of the problem, we would have to go through basically every single index pairing and do the multiplication, which would mean that we have to touch, all the elements in both vectors here. So that means that, runtime complexity wise, it would be big O of, n plus m, because this is going to be the biggest part here. And then what the space complexity is, we would have to store both those vectors for both of them. So it would be big O of n for the first vector and big O of m for the other one. And since we're doing, we're using both of them, so it's big O of n plus m. And I apologize if I said earlier that it was actually a big O of n. It's actually n plus m because we have to consider the second vector. So this is going to be our runtime complexity. And this is how you solve this problem. This is the solution that your interviewer is looking for. If you just say the hash map solution, which a lot of people, if you look at the kind of discussion here in the comments, they'll tell you, where is it? I had my Facebook on-site, the interviewer didn't accept the hash map solution. So, you can't just say, oh, I'm going to use the hash map solution and that's, job done. You can start with that, but they will most likely push you for this tuple solution. And this is the answer that you're going to want to give. And the way to approach this problem is, I think the best way is simply to tell them about the naive solution, which is really simple. Don't write any code for it. Don't waste time. Then mention the hash map solution, but say, okay, well, if our hash map sucks, then, we would have these issues. And then say, well, the answer that I want to go with is the tuple solution, because then we don't have to worry about the hash map. Of course, it is a little bit more complicated to implement, but, that is the trade-offs for our algorithm. This is going to show that you understand that, the hash map may not always be perfect. And it's going to show that you've weighed the pros and the cons of your solutions, which is definitely the hiring signal that any interviewer is looking for. They don't care that you can solve the problem. They want to test your critical thinking ability and your ability to weigh the pros and the cons of approaches, because this is what's going to happen in any real life scenario. People complain, oh, LeetCode problems aren't indicative of reality. You're never going to use these algorithms in real life. Okay, that may be true to an extent, but the problem solving process that you go through with these questions, and this is a perfect example of having to weigh the pros and the cons of two approaches and then making a decision which makes more sense, is the signal that you're really looking for. You may make some mistakes in the implementation, But if your communication is clear and you're able to explain why you went with one solution, and then you also weighed the pros and the cons effectively, your interviewer will most likely overlook, okay, you made a small bug here, maybe you said the time complexity incorrectly. That signal for them is going to be much stronger than you getting the coding perfectly like an absolute robot. So that is something to consider. Now, for the follow-up, I'm just going to mention if only one of the vectors is sparse, then what you would want to do is basically a binary search approach where you take the one that is smaller and then you search those indexes in the bigger one. And that would be your solution. Again, you can discuss with your interviewer, okay, at what point does it actually flip and make sense to use binary search here? Because there is some like value where, okay, even if one of them is sparse, but the other one, how sparse does it have to be, or like how big does it have to be for that point to make sense? I'm gonna stop rambling at this point. Basically, if he asks you the follow-up, what if only one of the vectors is sparse, then you want to go with the binary search approach to compute that. And you can still store it with the tuples. That's fine. You're just gonna have to perform a binary search. Anyway, if you've enjoyed this video, please like, comment, and subscribe. Check out my other videos if you're preparing for an on-site interview, and happy coding.